Tonight, we begin very close to home. Not among distant stars, not beside some enormous galaxy millions of light years away, but here, on the world beneath our feet. Take a quiet moment and imagine the Earth as it really is. Not as a city, not as a country, not as a map divided by borders, but as a small world, a sphere of rock and water, turning silently through the darkness of space. We spend most of our lives standing on the Earth without feeling its motion. The ground beneath you seems perfectly still. The room around you seems perfectly still. Even the night sky can give the impression that everything above us is simply hanging there, quietly waiting. But the Earth is never still. It is constantly moving through space. At this very moment, the planet beneath you is rotating, and while it rotates, it is also traveling around the sun, and the sun itself is moving through the Milky Way. So even while you are lying completely still, you are traveling through the universe. The Earth carries you with it. The speed of that motion depends on where you are standing. Because the Earth is rotating around its axis, different places on its surface move at different speeds. Near the equator, the surface travels much faster than it does near the poles. And yet, you do not feel this motion. You do not feel the ground rushing beneath you. You do not feel the rotation. There is no sensation of being carried through space. And perhaps that is one of the strangest things about living on a planet. We are moving constantly, and stillness is what it feels like. The Earth also has another enormous journey. Once every year, our planet completes an orbit around the sun. 1 year, 12 months, a period so familiar that we rarely think about what it actually means. But every birthday, every winter, every summer, every sunrise and sunset is part of a much larger journey. The Earth is traveling around a star, and we are traveling with it. The seasons we experience are connected to another subtle feature of our planet. The Earth's axis is tilted. It is not standing perfectly upright as it travels around the sun. That tilt changes how sunlight reaches different parts of the planet throughout the year. And from that simple geometry comes one of the great rhythms of life on Earth. Spring, summer, autumn, winter. The changing angle of sunlight. The changing length of days. The changing temperatures. The migrations of animals. The growth and disappearance of plants. So many familiar patterns are connected to something as simple as the orientation of a spinning world. And yet, for all the vastness of the Earth, the atmosphere surrounding it is remarkably thin. When we look at photographs of our planet from space, the atmosphere can appear as a delicate blue line around the edge of the world. That thin layer contains the air we breathe. It helps regulate temperature. It protects the surface from much of the dangerous radiation and energetic particles arriving from space. It is the environment in which every human life has ever existed. And, compared with the size of the planet itself, it is incredibly thin. A fragile-looking layer surrounding a world that carries billions of lives. Most of that world is covered by water. Oceans stretch across enormous portions of the Earth's surface. From space, this is one of the first things that becomes obvious. The Earth is blue. Not because blue is simply the color of our planet, but because water dominates its surface. And those oceans are not merely beautiful. They are part of the enormous systems that regulate our climate. They store heat. They move energy around the planet. They interact with the atmosphere. They support countless forms of life. Much of what makes Earth suitable for us is connected to the presence of liquid water. And beneath all of this, there is another invisible structure surrounding the planet: the Earth's magnetic field. It is generated deep inside the planet by movements within its outer core. We cannot see it with our eyes. We cannot touch it. And yet, it extends far beyond the surface of the Earth. It interacts with the solar wind, the constant stream of charged particles flowing outward from the sun. The magnetic field helps shield our planet from much of that environment. And when particles from the solar wind interact with Earth's magnetic field and upper atmosphere, the result can sometimes be one of the most beautiful sights in the night sky. The auroras, curtains of light appearing over the polar regions, a reminder that even something invisible can shape what we see above us. Deep beneath the surface, the Earth becomes even stranger. The planet may appear calm from above, but inside it, there is tremendous heat. The Earth's core remains extremely hot. Some of that heat is left over from the formation of the planet billions of years ago. Some comes from radioactive elements slowly decaying inside the Earth. And that internal energy continues to influence the planet today. It drives processes deep beneath our feet. It contributes to the movement of the Earth's crust. It helps power the geological activity that has been reshaping the surface for immense periods of time. The mountains beneath which we live, the oceans, the continents, the valleys, the rocks, all of them belong to a planet that has been changing for billions of years. The Earth is not a finished object. It is a world still in motion, still changing, still carrying the history of everything that happened before us. And this brings us to another remarkable fact. The Earth is incredibly old, far older than human civilization, far older than written history, far older than cities, far older than agriculture. The planet formed roughly 4.5 billion years ago. For almost all of that time, there were no humans here, no languages, no countries, no roads, no lights glowing across the night. The Earth existed without us. Mountains rose and eroded. Oceans formed and changed. Life appeared. Species evolved. Entire ecosystems emerged and disappeared. And through all of it, the planet continued turning. When we think about human history, even thousands of years can feel enormous. We look backward and see ancient civilizations, ancient cities, ancient monuments, generations separated by centuries. But compared with the age of the Earth, human history occupies only a tiny fraction of the story. And the strange thing is, every human being we know of, every person who has ever lived, every civilization, every language, every story, every dream, has existed on this one small world. All of human history happened here. Every ancient fire, every first step, every conversation beneath the night sky, every telescope ever built, every spacecraft ever launched, every person who has ever looked toward the stars and wondered what might be waiting beyond them, was standing somewhere on this planet. Think about that for a moment. The universe contains an enormous number of stars. Countless worlds may exist around them. Galaxies stretch across distances that are almost impossible to imagine. And yet, our entire known human story began on this one world, a small planet orbiting one ordinary star, inside one galaxy, in a universe far larger than we can easily comprehend. And perhaps that is the right place to begin our journey, not with the largest things, but with the smallest place we know personally, home. Because before we can understand the scale of the universe, we have to remember just how remarkable this little world already is. The ground beneath you is moving. The planet is rotating. The Earth is orbiting the sun. The sun is traveling through the galaxy. And somewhere beyond all of that, the universe continues expanding. For now, though, we can stay here, on Earth, under the atmosphere, beside the oceans, on a planet warmed by an ancient star, a planet that has carried life for billions of years, and humanity for only a brief moment. And beyond this world, there is another familiar object, waiting in the darkness, a smaller world, our nearest natural neighbor, a world that has watched the Earth for billions of years, the Moon. So when you are ready, let us slowly leave the Earth behind and begin our journey toward it. Now, let us leave the Earth behind. Slowly, far below us, the oceans become smaller. The continents begin to lose their familiar shapes. The atmosphere becomes a thin blue line, and the Earth itself becomes a small world floating in darkness. Ahead of us, another world is waiting. The Moon, our nearest natural neighbor, a familiar presence in the night sky. And yet, from a distance, it is an entirely different world. The Moon probably began its existence in one of the most violent events in the early history of Earth, billions of years ago. When the solar system was still young, the Earth was struck by a massive object. The collision was enormous. Material from the young Earth and the impacting body was thrown into orbit. Over time, that debris gathered together, and from it, the Moon was formed. We cannot watch that ancient event happen. It occurred long before human beings existed, long before there were oceans as we know them today, long before life had taken anything resembling its modern form. But every night, we can see the result, the Moon. And the Moon has been with the Earth for an extraordinarily long time. For billions of years, it has traveled around our planet. And over that immense span of time, something very interesting happened. The Moon became gravitationally locked to Earth. This is called tidal locking. The Moon rotates around its own axis, but it rotates at just the right rate to keep the same side facing Earth. That is why, whenever you look toward the Moon, you are almost always looking at the same lunar hemisphere. It can feel strange when you first think about it. The Moon is rotating. It is orbiting Earth. And yet, the same side remains turned toward us. It is not because the Moon does not rotate. It does. It is because its rotation and its orbit are synchronized. One rotation takes about as long as one orbit around Earth. And that simple relationship has shaped the way humanity has experienced the moon throughout history. The side we see is covered in an ancient landscape. Craters, mountains, plains, ridges, valleys. The moon has almost no atmosphere capable of protecting its surface in the way Earth's atmosphere protects ours. There is no thick layer of air to burn up incoming objects. There is no rain to wash landscapes away. There is no wind like the winds we experience on Earth. As a result, the moon preserves an extraordinary record of impacts from the distant past. Some craters are incredibly old. They have remained visible for immense periods of time. The moon is, in a sense, a geological memory. A world where traces of ancient events can remain on the surface for billions of years. And this creates one of the strangest places humans have ever visited: the lunar surface. When astronauts walked there, they left footprints behind. Those footprints were not quickly erased by wind or rain. There is no weather system sweeping across the lunar surface. No atmosphere carrying dust from one place to another in the way it does on Earth. So those marks may remain for extraordinarily long periods of time. A human footprint preserved on another world. A tiny reminder that, for a brief moment, someone from Earth stood there. But the moon has influenced our home even while remaining hundreds of thousands of kilometers away. Its gravity pulls on the Earth, and one of the most visible results is the movement of our oceans. The tides. The oceans rise and fall as the gravitational interactions between the Earth, the moon, and the sun continuously reshape them. The moon is the dominant source of the tidal forces affecting Earth's oceans, and every day, the coastlines of our planet respond quietly, predictably, over and over again. The relationship between Earth and moon is not completely static. The moon is slowly moving away from Earth, only a small amount each year, but over immense periods of time. Small changes accumulate. The moon is gradually becoming more distant, and the Earth-Moon system continues to evolve. Even something that appears permanent in the night sky is slowly changing. There is another remarkable relationship between the Earth, the moon, and the sun: eclipses. Sometimes, the moon passes directly between Earth and the sun. From certain places on Earth, the moon can appear to cover the sun completely. A total solar eclipse. It is one of the most striking sights in nature. Daylight fades, the sky becomes strangely dark, and, for a brief moment, the sun's brilliant outer atmosphere becomes visible around the dark silhouette of the moon. What makes total solar eclipses possible is a remarkable coincidence. The sun is vastly larger than the moon, but it is also vastly farther away. The moon is much smaller, but it is much closer to us. From Earth's surface, their apparent sizes in the sky can sometimes be remarkably similar. And that coincidence allows the moon to cover the visible disk of the sun. It is not because the two objects are actually similar in size. They are not. It is simply the result of their relative sizes and distances. For humanity, the moon has never been merely an object in the sky. It became a destination. Humans eventually traveled there. Spacecraft crossed the distance. Astronauts descended to the surface. Scientific instruments were placed on the ground. Samples of lunar material were collected and brought back to Earth, and countless objects remain there today. Equipment, experiments, vehicles, landing hardware, and other human-made artifacts. A small collection of traces left behind on another world. When we look at the moon tonight, we are therefore looking at something that connects several different stories. The ancient history of the Earth, the violent formation of the early solar system, the gravitational relationship between two worlds, the tides of our oceans, the changing geometry of eclipses, and the beginning of human exploration beyond our planet. The moon has watched the Earth for billions of years, long before humanity existed. It was already there, before our first cities, before our first written words, before anyone knew what a planet was. The moon was already crossing the sky. And now, for the first time in the history of our species, we have reached it, but the moon is only our nearest neighbor. Beyond it, there is an object whose influence reaches through the entire solar system, a star so much larger than Earth that its gravity holds the planets in their great orbital paths, a star that provides almost all the energy that powers life on our world. A star that has been rising above the Earth long before humans ever learned to name it, the Sun. And now, let us leave the moon behind and slowly turn toward the light. And now, the moon slowly falls behind us. The Earth becomes smaller, and ahead, there is a light so familiar that we rarely stop to consider just how extraordinary it is. The sun. Every morning, we see it rise. Every evening, we watch it disappear beyond the horizon. It feels ordinary, almost permanent. But from the distance of space, the sun reveals itself as something enormous. A star, our star, the center of the planetary system that has been our home for billions of years. Almost all of the mass in the solar system belongs to the sun. The planets, the moons, the asteroids, the comets, all of them together make up only a small fraction of the total mass. The sun dominates. Its gravity reaches across immense distances, holding the planets in their orbits. Mercury circles close to it. Venus follows. Earth travels farther out. Mars beyond us. And then, the outer planets continue into the darkness, all of them connected by the same star. And although the sun is enormously far away, its light reaches Earth surprisingly quickly. It takes a little more than 8 minutes for sunlight to travel from the sun to our planet. That means that when you see sunlight, you are seeing light that left the sun several minutes earlier. The sun you see in the sky is always the sun from a few minutes in the past. The journey of that light begins deep inside the sun. At its center, the temperature and pressure are extraordinary. The sun's core is dense and incredibly hot. There, hydrogen nuclei are pushed together under immense pressure. Through nuclear fusion, hydrogen is transformed into helium, and in the process, energy is released. That energy begins a very long journey outward. It moves through the interior of the sun, passing through layers of incredibly dense material, before eventually reaching the surface. And from there, it escapes into space. Some of that light travels across the solar system, and a tiny fraction reaches Earth. The visible surface of the sun is called the photosphere. This is the layer that gives us the familiar appearance of the sun. But even this seemingly smooth surface is constantly changing. The sun is not a solid ball. It is a vast sphere of extremely hot plasma. Its surface is alive with movement. Patterns rise and fall. Energy moves through the star. Magnetic fields twist and change. And sometimes we can see the effects of those magnetic fields as dark regions. Sunspots. Sunspots appear darker because they are cooler than the surrounding areas of the photosphere. They are still extraordinarily hot, but compared with the surrounding surface, they appear dark, and their appearance is connected to the sun's powerful magnetic activity. The sun's magnetic field is constantly changing. It can become tangled, stretched, twisted, and sometimes that stored magnetic energy is released in enormous bursts. The sun is not simply shining quietly into space. It is continuously sending particles outward. A stream of charged particles flows away from the star. We call this the solar wind. It travels through the solar system, passing the planets and continuing far beyond them. The solar wind creates an enormous region around the sun, a vast bubble shaped by the star's influence, and our entire planetary system exists inside that environment. Sometimes, the sun becomes especially active. Large eruptions can release tremendous amounts of energy and charged particles. When these events reach Earth, they can interact with our planet's magnetic field and upper atmosphere. The consequences can be beautiful. Auroras may become brighter and appear farther from the polar regions. But powerful solar storms can also create serious problems. They can interfere with satellites. They can affect radio communication. They can disturb navigation systems. And, in extreme circumstances, they can even interfere with electrical infrastructure on Earth. It is easy to think of the sun as a completely stable object. It rises every morning. It sets every evening. Its light has been reaching Earth for billions of years. But the sun is changing too. It is a star with a life cycle. It was born billions of years ago, and it will not remain exactly as it is forever. The sun still has billions of years ahead of it. For a very long time, it will continue producing energy through hydrogen fusion in its core. But eventually, the hydrogen available in its core will become depleted. The sun will then begin to change. Its outer layers will expand dramatically. Its future will be very different from the quiet star we see today. Eventually, the sun will reach the final stages of its stellar life. That future is unimaginably far away. So far away that it has almost no meaning on the scale of a human lifetime. Civilizations will rise and disappear long before then. Assuming humanity continues to exist for that long, entire continents will change. Species will appear and vanish. Languages will be forgotten. New civilizations may replace everything we know. And through all of it, the sun will continue shining. There is something deeply humbling about that. The star above us is both familiar and enormous. We depend on it for nearly everything. Its light drives Earth's climate. Its energy supports photosynthesis. Plants capture sunlight and transform it into chemical energy. Food webs begin there. Oceans are warmed by it. Weather is influenced by it. The seasons depend upon the geometry of our orbit and the tilt of our planet. Even the rhythm of daily life, the distinction between day and night, begins with the presence of this distant star. And yet, the Sun is only one star, one among an enormous number of stars in the universe. From Earth, it looks special because it is our star. But if we could travel far enough away, the Sun would gradually become another point of light, one star among countless others. And this is where our perspective begins to change. Because the solar system that feels so enormous from Earth is actually very small compared with the universe beyond it. The Sun dominates our local neighborhood, but beyond the orbit of the outer planets, the darkness becomes deeper, the distances become larger, and the familiar worlds become fewer. Still, before we leave our star, take one final moment to imagine it from far away. A single glowing sphere in the darkness, surrounded by planets, moons, asteroids, comets, and one small blue world, where life learned to look back toward the star that made its existence possible. The Sun has been our light, our source of warmth, our clock, and the center of our cosmic neighborhood. But it is not the only world moving through this system. Around it, 8 major planets travel along their ancient paths, each one formed from the same primordial disk of material, and each one became something completely different. Some are small and rocky, some are enormous and gaseous, some are covered by crushing atmospheres, others are worlds of ice and extreme cold. They all belong to the same family. And now, slowly, we are going to leave the Sun behind and begin visiting those 8 worlds, one by one, starting with the small, scorching planet closest to the star, Mercury. And now, Mercury waits ahead of us, the smallest of the 8 major planets, the closest planet to the Sun, a world that circles our star at a distance where sunlight is many times more intense than it is on Earth. From here, the Sun would appear larger, brighter, more powerful, and Mercury itself would seem almost like a strange piece of ancient stone, covered in craters, silent beneath a black sky. Mercury is the closest planet to the Sun. Its orbit is much smaller than Earth's. Because it travels so close to the Sun, Mercury completes an entire orbit in only about 88 Earth days. A year on Mercury is therefore surprisingly short, but its days are very different. The planet rotates slowly compared with Earth, and because of the way its rotation and orbit are synchronized, one solar day on Mercury lasts far longer than its year. It is a world where the passage of time feels completely different from what we experience at home. Mercury is a small, rocky planet. Its surface is covered with craters created by impacts that occurred over immense periods of time. There is no thick atmosphere to erase them, no oceans to reshape them, no forests or rivers to cover the ancient scars. Like the Moon, Mercury preserves much of its history directly on its surface, a landscape written in stone. And yet, Mercury is not the hottest planet in the solar system. That title belongs to the next world, Venus. From a distance, Venus can look almost peaceful. It is bright in the Earth's sky. It is often visible near sunrise or sunset. For centuries, people watched it and imagined another world hidden beneath its clouds. But beneath those clouds, Venus is extraordinarily hostile. Venus possesses an incredibly thick atmosphere. It is composed mostly of carbon dioxide, and the pressure at its surface is enormous. The atmosphere traps heat so efficiently that Venus has become the hottest planet in the solar system. Even though Mercury is closer to the Sun, Venus is hotter. Its dense atmosphere creates a powerful greenhouse effect. Heat enters and is trapped within the atmosphere. The result is a surface environment hot enough to melt lead. It is difficult to imagine such a world when looking at Venus from Earth. From here, it is simply a bright point of light. Beautiful, quiet, almost delicate. But beneath its clouds, the planet is anything but gentle. Its surface is a reminder that the appearance of a world from far away can tell us very little about what it is actually like. And then, there is Earth, the third planet from the Sun, the world we already know. But from this distance, Earth becomes something else. A small blue planet between two very different neighbors. One world scorched by the sun, another covered by an extreme atmosphere, and between them, a planet with oceans, clouds, forests, ice, and life. Beyond Earth, we encounter Mars, a smaller world, cold, dry, and covered in reddish dust. Mars has fascinated humanity for generations. Its surface contains enormous valleys, ancient river channels, polar ice, and volcanoes that reveal a distant geological past. Among them is Olympus Mons, the largest known volcano in the solar system. It rises far above the surrounding Martian landscape, a monument to a time when Mars was much more geologically active than it is today. Mars is very different from Earth. Its atmosphere is extremely thin. Its surface is cold. Liquid water is not stable on the surface under ordinary present-day conditions. And yet, the planet contains evidence that water once flowed across its surface. Ancient valleys, minerals formed in the presence of water. Features that suggest Mars was once a much different world. A world that may once have possessed environments capable of supporting conditions suitable for life. Leaving Mars behind, the solar system suddenly becomes much larger. Ahead of us is a planet so enormous that it could contain more than 1,000 Earths by volume. Jupiter, the largest planet in the solar system. Jupiter is a gas giant. It does not have a solid surface like Earth. Its atmosphere becomes denser and denser as we descend. Clouds stretch across enormous distances. Storms move through its atmosphere. Bands of different colors circle the planet, and among them, one feature has become almost legendary: the Great Red Spot. The Great Red Spot is a gigantic storm. It has been observed for centuries. It is much larger than Earth, and it has persisted for an extraordinary amount of time. Storms on Earth eventually weaken and disappear, but Jupiter's atmosphere operates under very different conditions. Its immense size, rapid rotation, and complex atmospheric dynamics allow enormous storms to persist for long periods. Jupiter is more than just a giant planet. It is a miniature system of its own. It has many moons. Some of them are worlds, with environments almost as fascinating as the planets themselves. But we will visit those later. For now, we continue outward. Beyond Jupiter, Saturn appears. Another giant planet. But Saturn has something that makes it immediately recognizable. Its rings. From a distance, they seem almost impossibly delicate. Thin bands of brightness surrounding a massive world. But the rings are not a single solid structure. They are made primarily of countless pieces of ice and rocky material, orbiting Saturn independently. Some particles are tiny, others are much larger. Together, they create the magnificent system we see from afar. Saturn itself is enormous. Like Jupiter, it is a gas giant. Its atmosphere contains powerful winds and complex patterns. But the rings are what have made Saturn one of the most recognizable worlds in the solar system. A planet surrounded by a vast cosmic disk turning silently through space. Further away, the sunlight becomes weaker. The planets receive less energy from the sun, and eventually, we reach Uranus, a world unlike the others. Uranus has an extraordinary axial tilt. Its rotation is almost sideways compared with the orientation of most planets. Because of this unusual tilt, its seasons are extreme. During its long journey around the sun, different hemispheres can experience years of unusual sunlight patterns. It is one of the strangest orientations among the major planets. Uranus is also an ice giant. Its composition is very different from the rocky planets closer to the sun. It contains large amounts of materials such as water, ammonia, and methane in forms quite different from what we experience on Earth. Methane, in its upper atmosphere, absorbs certain wavelengths of light, helping give Uranus its blue-green appearance. A distant world, cold, quiet, and almost unimaginably far from our home. And finally, at the outer edge of the 8 major planets, we reach Neptune, the farthest major planet from the Sun. Here, the sunlight is faint, the temperatures are extremely cold, and yet the atmosphere can be extraordinarily violent. Neptune possesses some of the fastest winds known among the planets. Cloud systems can race around the planet at tremendous speeds. It is a strange contrast, a world receiving very little sunlight, yet possessing a remarkably dynamic atmosphere. From Mercury to Neptune, the 8 major planets form an extraordinary family. They all formed from the same broad disk of material around the young sun. And yet, they became completely different worlds. One is small and heavily cratered. Another is wrapped in a crushing atmosphere. One contains vast oceans and life. Another preserves evidence of ancient rivers. Then come the giant planets, worlds so large that their atmospheres become almost planetary landscapes of their own. And farther away, the cold blue giants. Each planet represents a different solution to the same cosmic process, the same basic ingredients: rock, metal, gas, ice, dust, heat, gravity, time, and from those ingredients, nature created 8 very different worlds. Perhaps that is one of the most beautiful things about the solar system. It is not simply a collection of planets. It is a collection of possibilities. 8 major worlds, all orbiting the same star, yet each carrying its own history, its own atmosphere, its own climate, its own geological story, its own relationship with sunlight. And even these 8 worlds are only part of the story, because around the planets there are other worlds. Some are small, some are enormous, some are covered in ice, some are covered in volcanoes, some may hide oceans beneath their frozen surfaces, and some may contain environments unlike anything we have ever experienced on Earth. The moons. So now, leaving the planets behind for a moment, let us begin exploring the strange worlds that travel beside them. Now, the planets slowly continue along their ancient paths, but around some of them, other worlds are moving too. Moons. Some are tiny, some are enormous, some are little pieces of rock and ice. Others are worlds so complex that, if they were orbiting the sun by themselves, we might easily think of them as planets. And perhaps the strangest thing about the moons of the solar system is how different they can be. Jupiter has an enormous family of moons. More than 90 are currently known. Some are little more than irregular pieces of rock captured by Jupiter's enormous gravity. Others are large enough to have their own complex geological histories. 4 of them became especially famous: Io Europa, Ganymede, and Callisto. Together, they are known as the Galilean moons. They were observed by Galileo Galilei more than 4 centuries ago, and their discovery changed our understanding of the solar system, because suddenly it became clear that not everything in the heavens revolved around Earth. There were other worlds circling another planet. One of those worlds is Io, and Io is unlike almost anywhere else we know. It is intensely volcanic. Its surface is constantly being reshaped by eruptions. Mountains rise, lava flows, volcanic material is thrown into the thin environment surrounding the moon. Io is caught in a gravitational tug-of-war. Jupiter's enormous gravity pulls on it, while the other large moons also influence its orbit. That constant gravitational flexing generates enormous amounts of internal heat, and that heat drives Io's extraordinary volcanic activity. Imagine standing on a world where the landscape itself is constantly being rewritten. A mountain could form from volcanic activity. A surface covered in lava could cool, only to be covered again by another eruption. The familiar idea of a quiet, frozen moon disappears. Io is alive with geological activity, a small world, but one of the most volcanically active places known anywhere in the solar system. And then, only a little farther away, there is Europa. At first glance, Europa may seem much quieter. Its surface is covered by ice, a bright, frozen shell marked by long cracks and strange patterns. But beneath that ice, there may be something extraordinary: a global ocean of liquid water. Scientists have strong evidence that Europa contains an ocean beneath its icy crust. The water is hidden, protected from the vacuum of space by a thick layer of ice. And beneath that frozen surface, the ocean could contain more liquid water than all of Earth's oceans combined. We cannot simply look down and see it. We have to study the moon indirectly, its magnetic environment, its surface, its gravitational behavior, the way it interacts with Jupiter. Piece by piece, a picture begins to emerge, a frozen world, with an ocean hidden underneath. Europa is one of the places where the search for life beyond Earth becomes especially interesting. Life, as we know it, requires certain ingredients. Liquid water is one of them. Energy is another. And chemistry provides the materials from which living systems can develop. Europa may possess all three in some form. That does not mean life exists there. We have not discovered evidence of life on Europa, but the possibility of a hidden ocean makes the moon one of the most fascinating environments in the solar system. Then there is Ganymede, the largest moon in the solar system. In fact, Ganymede is larger than Mercury. That alone makes it remarkable. It is a world large enough to have its own complex interior, and it even possesses its own magnetic field. A moon with a magnetic field of its own. Ganymede's surface contains regions of different ages. Some areas are darker and heavily cratered. Others are brighter and appear to have been reshaped by geological processes. Beneath the surface, scientists believe Ganymede may also contain layers of liquid water. Once again, a seemingly frozen world may hide an enormous amount of water beneath its surface. And then there is Callisto, a quieter-looking moon, but one with a remarkably ancient surface. Callisto is covered with craters. Many of them are extremely old. Its landscape preserves a record of impacts that occurred during the early history of the solar system. It is almost like looking backward through time. Each crater is a reminder of something that happened long ago, when the solar system was younger, and the environment around these worlds was far more chaotic. Leaving Jupiter behind, we approach Saturn, and Saturn has its own extraordinary family of moons. More than 100 are known, and once again, the diversity is remarkable. Some are tiny, some are irregular, some are icy, and some possess atmospheres and surface environments that make them feel almost like miniature planets. Among them, two stand out, Enceladus and Titan. Enceladus is small. Its surface is covered in bright ice, but beneath that frozen exterior, there appears to be a subsurface ocean, and Enceladus does something particularly remarkable. It sends material into space. Jets of water vapor and icy particles erupt from fractures near its south pole. The material escapes from the moon and enters space. Some of it even contributes to Saturn's enormous E-ring. This means that scientists do not necessarily need to land on the surface and drill through kilometers of ice to investigate what may be happening beneath it. The ocean is revealing itself. Tiny particles of material are being thrown into space, where spacecraft can potentially study them. A hidden environment, leaving traces where we can reach them. And then there is Titan, perhaps one of the strangest moons in the entire solar system. Titan is larger than the planet Mercury. It has a thick atmosphere, rich in nitrogen. From a distance, its surface is hidden beneath a hazy orange atmosphere. But beneath that haze, Titan possesses landscapes that feel strangely familiar. Rivers, lakes, seas, clouds, rain. But there is an enormous difference. These are not water landscapes. Titan is so cold that methane and ethane can exist as liquids on its surface. The Moon has a methane cycle that, in some ways, resembles Earth's water cycle. Methane can evaporate. It can form clouds. It can fall as rain. It can flow across the surface. And it can collect in lakes and seas. Imagine standing beneath an alien sky, watching rain fall from the clouds. But the rain is not water. It is liquid methane. Titan is one of the few places in the solar system where we know of stable bodies of liquid on a planetary surface other than Earth. Its lakes and seas are enormous. Its atmosphere is thick. Its chemistry is complex. And its surface contains landscapes shaped by liquids flowing across the ground. It is alien. And yet, some of its processes feel strangely familiar. The moons of the solar system remind us that planets are not necessarily the most interesting worlds. A moon can have volcanoes. A moon can hide an ocean. A moon can possess a magnetic field. A moon can have an atmosphere. A moon can have lakes and seas. A moon can preserve a geological history older than almost anything on Earth. And perhaps the most exciting possibilities are hidden beneath the ice. Europa, Enceladus, Ganymede, and other icy moons throughout the solar system may contain environments that remain completely hidden from our direct view. Deep oceans, warm interiors, complex chemistry, places where liquid water can survive far from the warmth of the sun. This is important because it changes the way we imagine where interesting environments can exist. For a long time, it was natural to look toward planets that resemble Earth, a rocky surface, an atmosphere, temperatures that might allow liquid water. But the moons have given us another possibility. Perhaps a world does not need a warm surface to contain an interesting environment. Perhaps an ocean can exist beneath kilometers of ice. Perhaps energy can come from gravity rather than sunlight. Perhaps some of the most intriguing places in our cosmic neighborhood are worlds whose surfaces look completely frozen and lifeless. And there is something peaceful about that idea. A frozen moon, turning silently around a distant planet, its surface illuminated by weak sunlight, while far beneath the ice, an entire hidden ocean may be moving in darkness. A world within a world. But even the moons are not the end of our solar system. Beyond the major planets and their satellites, there are countless smaller worlds, asteroids, comets, dwarf planets, fragments of ancient material, frozen bodies traveling through enormous regions of darkness. Many of them have never been visited by a spacecraft. Some may preserve material left over from the birth of the solar system itself. So now, we will leave the giant planets and their strange moons behind. We will travel outward, toward the smaller worlds, the forgotten worlds, the remnants of a solar system that formed billions of years ago, and whose oldest pieces may still be quietly traveling through the darkness. The giant planets are now behind us. Their moons become smaller in the distance. And ahead of us, the solar system begins to feel much emptier. The familiar planets occupy only a tiny portion of the space surrounding the sun. Beyond them, there are countless other objects. Some are large enough to be rounded by their own gravity. Some are irregular pieces of rock. Some are covered in ice. Some travel on long, elongated orbits that bring them close to the sun only once in many years. And some may have spent almost their entire existence in the darkness. When we imagine the solar system, it is easy to picture 8 planets moving through empty space. But that picture leaves out an enormous amount. There are millions of known and estimated smaller bodies spread throughout our planetary system. Asteroids, comets, dwarf planets, fragments of rock and ice, objects left behind from the formation of the planets. They are the remnants of an ancient process that began more than 4 billion years ago. One of the most famous regions is the asteroid belt. It lies between the orbits of Mars and Jupiter. From movies and stories, it is sometimes imagined as a dense field of enormous rocks packed closely together. But the real asteroid belt is much more spacious. Individual objects can be separated by enormous distances. And yet, millions of bodies are believed to inhabit this region. Some are tiny. Some are several hundred kilometers across. Together, they form one of the great populations of leftover material in the solar system. Among them is Ceres. Ceres is the largest object in the asteroid belt. It is also classified as a dwarf planet. Unlike the small, irregular asteroids surrounding it, Ceres is large enough for its own gravity to have shaped it into a nearly spherical world. It has been studied by spacecraft, and beneath its surface, scientists have found evidence that water and water-rich materials have played an important role in its history. Ceres is a reminder that the solar system does not have a simple boundary between planets and everything else. There are worlds of many sizes. Some are large enough to become round. Some are smaller. Some are almost entirely made of ice. Others are mostly rock. And many occupy the space between our familiar categories. Then, there are comets, perhaps the most poetic objects in the solar system. Comets are made primarily of ice, dust, and rocky material. They are ancient leftovers from the formation of the planetary system. In a sense, a comet is a fragment of the early solar system, still traveling through space. When a comet remains far from the sun, it can look like little more than a frozen body moving silently through darkness. But when its orbit brings it closer to the sun, everything changes. Solar heating begins to affect the ice. Gas and dust escape from the surface. A cloud called the coma develops around the nucleus, and material is pushed outward, creating the familiar tail. The tail of a comet is one of the most beautiful sights in the night sky, but it is important to remember that the tail is not simply a trail left behind by the comet as it moves. Its direction is strongly influenced by sunlight and the solar wind. As the comet approaches the sun, material escaping from its surface interacts with the environment around the star. The result can be a long structure stretching through space. Sometimes, the tail can become enormous, and yet, the comet itself may be relatively small, a dark nucleus, often only a few kilometers across, a tiny body producing a structure that can stretch millions of kilometers through space. It is another example of how the sun can transform even the smallest objects in its neighborhood. Farther outward, the familiar solar system becomes colder. The sunlight weakens. The worlds become more distant. And eventually, we encounter Pluto. For decades, Pluto was taught to generations of children as the ninth planet. Today, it is classified as a dwarf planet, but its new classification did not make it any less fascinating. Pluto is a small, frozen world. Its atmosphere is extremely thin and changes dramatically as Pluto moves along its orbit. The planet's surface contains enormous plains of nitrogen ice, as well as mountains made largely of water ice. And, because Pluto is so cold, water ice behaves more like rock than the liquid water we know on Earth. Its landscape is frozen, ancient, and remarkably complex. When the New Horizons spacecraft flew past Pluto, humanity saw this distant world in detail for the first time. We discovered mountains, valleys, glaciers of nitrogen ice, large regions with surprisingly varied landscapes. The distant point of light that had once seemed almost featureless became a real world. Pluto also has a large companion moon, Charon, and Charon is unusual. It is enormous compared with Pluto. The two worlds are so similar in scale that their relationship is unlike the usual picture of a large planet with a much smaller moon. Their shared center of mass lies outside Pluto itself. They move around a common point in space, creating a system that is almost like a pair of worlds orbiting together. Beyond Pluto, the solar system continues. There is no sudden wall, no sharp boundary. Instead, the population of icy bodies continues outward. One of the most important regions is the Kuiper Belt, a broad region beyond Neptune, filled with icy objects left over from the early solar system. Pluto is part of this distant population, and there are many other worlds out there, most of which we have never visited. The Kuiper Belt is extraordinarily far from the sun. At those distances, the sunlight is weak, temperatures are extremely low, and objects can remain frozen for billions of years. That makes these distant bodies especially valuable to scientists. They may preserve materials that have changed very little since the solar system formed. But even the Kuiper Belt may not be the end. Farther away, there may be an enormous, extremely distant reservoir of icy objects. We call this the Oort cloud. Unlike the Kuiper Belt, the Oort cloud is thought to surround the solar system in a vast, spherical distribution. If it exists, as models suggest, its outer boundary could extend astonishingly far from the sun. So far that the distance between the sun and the nearest stars begins to become a meaningful comparison. The Oort cloud has never been directly observed as a collection of individual objects. It remains a scientific model based largely on the orbits of long-period comets. These comets can travel enormous distances from the sun, returning only after thousands or even millions of years. Their paths suggest that a distant reservoir of icy bodies may surround the solar system. Imagine that a comet leaves the inner solar system and continues outward, past the planets, past the Kuiper Belt, into darkness, far beyond anything we could easily picture. And then, after an immense journey through space, it begins falling back toward the sun, returning to the place where its story began. The farther we travel, the more the solar system stops looking like the neat diagram we learned as children. There are no simple borders, no empty edge. Instead, there is a gradual transition from planets to moons, to asteroids, to comets, to distant icy worlds, and eventually to the enormous space between our star and every other star. And that distance is difficult to comprehend. The planets are separated by millions or billions of kilometers, but the stars are separated by distances measured in light years. A light year is the distance light travels in 1 year, and light moves incredibly quickly. Yet even light requires years to cross the space between neighboring stars. Our solar system is therefore only one small island, floating inside a much larger cosmic ocean. The sun remains behind us now. The planets are becoming distant. The outer worlds fade into darkness. And ahead, for the first time on our journey, there is no nearby planet waiting for us. No moon, no familiar world, only stars. The space between stars is not completely empty. There is gas, dust, particles, magnetic fields, radiation, and countless objects moving through the darkness. But compared with the crowded environments we have just left, it is an enormous expanse, and somewhere beyond that darkness, there are other suns, other planetary systems, other worlds. Some may resemble nothing we have ever imagined. Others may be strangely familiar, but all of them are separated from us by distances that make the solar system seem incredibly small. The sun, which once appeared enormous, is becoming just another point behind us. And this is the moment when our journey truly begins to leave home. Because beyond the solar system, there are stars, not just a few, but hundreds of billions within our galaxy alone, each one potentially carrying its own history, its own planets, its own worlds, its own story. So take a final look back. Behind us, the solar system is still there. The Earth, the Moon, the planets, the moons, the asteroids, the comets, all orbiting one ordinary star, all belonging to one small region of the galaxy. And ahead, the stars are waiting. The distance between them is immense. The journey will take us far beyond anything our ancestors could have imagined, because now we are leaving the solar system, and, for the first time, we are going to look at the stars themselves. The solar system is now far behind us. The planets have disappeared into the darkness. Even the distant icy worlds are becoming difficult to imagine. And ahead, there are stars, not worlds orbiting our sun, but other suns, other places where planets may exist, other systems separated from ours by distances so enormous that the word far begins to lose its meaning. The distance between the stars is vastly greater than the distances between the planets. Even the outer reaches of our solar system are tiny compared with the space separating one star from another. Earth is only about 8 light minutes from the Sun. The outer planets are hours away by light, but the nearest stars are years away, and that difference changes everything. Light travels faster than anything we know. It moves at about 300,000 kilometers every second. And still, the nearest star system beyond our Sun is more than 4 light years away. That means even light needs more than 4 years to cross the distance. For a spacecraft traveling far more slowly than light, the journey would take much longer. This is one of the most important differences between exploring our planetary system and exploring the galaxy. To reach Mars, we are crossing a distance within one star system. To reach another star, we are crossing the space between stars. It is not simply a longer journey. It is a completely different scale of travel. And the star waiting beyond our own is not necessarily an extraordinary object. In many ways, our Sun is a relatively ordinary star. It is a yellow dwarf, a star of moderate size and mass, shining steadily for billions of years. There are stars that are much smaller. There are stars that are much larger. There are stars that are cooler. There are stars that are dramatically hotter. And there are stars that live for vastly different lengths of time. Some stars are smaller than the Sun, much smaller. Red dwarfs are the most common type of star in the Milky Way. They are relatively cool and faint compared with the Sun. Because they burn their fuel so slowly, they can remain active for extraordinarily long periods. Some may continue shining for trillions of years, a timescale so long that the current age of the universe is almost impossible to compare with it. Other stars are enormous. Some are hundreds of times larger than the Sun. Their surfaces can be thousands of times larger in area. Their masses can be many times greater, and their brightness can exceed that of the Sun by enormous amounts. But there is a trade-off. The larger and more massive a star is, the more quickly it consumes its nuclear fuel. A massive star may shine brilliantly, but its life can be much shorter than that of a small red dwarf. This means that stars do not all experience time in the same way. A small star can exist quietly for extraordinary periods. A massive star can burn intensely and disappear from the cosmic stage after only a fraction of that time. The universe contains stars living at different speeds, some barely changing across immense stretches of time, others racing through their lives. But where do stars come from? They begin in enormous clouds, clouds of gas and dust, drifting through interstellar space. Some of these clouds can stretch across enormous distances. They may contain enough material to form thousands or even millions of stars. Inside these clouds, gravity slowly gathers material together. A region becomes denser. More gas falls inward. The concentration grows. As material accumulates, the temperature rises. Eventually, a young star begins to take shape. A process that begins quietly, over enormous periods of time. Stars are therefore not permanent lights that have simply existed forever. They are born, they evolve, and eventually, they die. Each one follows a path determined largely by its mass. And one of the most remarkable things about a star is that we can learn about its physical properties simply by observing its light. One of the clues carried by starlight is color. The color of a star tells us something about its temperature. Hotter stars tend toward white or blue colors. Cooler stars appear more orange or red. The difference is subtle when you look at the night sky, but it contains real information about the physical conditions on the surface of the star. When you look up at the stars, you are therefore not simply seeing points of light. You are seeing enormous physical objects, and the light reaching your eyes carries clues about them: temperature, composition, motion, age, distance, sometimes even the presence of planets. All of this information travels across space as light. Some stars live for billions of years. Our Sun is one of them. It has already existed for about 4.5 billion years, and it still has billions of years ahead. A human lifetime is tiny compared with the life of a star. Even entire civilizations can rise and disappear, while a star continues shining almost unchanged. But some stars can live for much longer. The smallest red dwarfs are incredibly efficient with their fuel. They consume hydrogen slowly, allowing them to remain stable for extraordinary periods. Some theoretical estimates suggest that the smallest red dwarfs could shine for trillions of years. That is hundreds of times longer than the current age of the universe. Think about that for a moment. The universe is about 13.5 billion years old. To us, that already feels almost unimaginably long. Human civilization is only a few thousand years old. Our species has existed for a tiny fraction of cosmic history. And yet, some stars may continue shining long after our entire present universe has become ancient. Perhaps somewhere in the distant future, a civilization could look toward one of these small red stars and consider it an ancient companion, a star that was already shining when the universe was much younger, and that will continue shining long after many other stars have disappeared. For now, the night sky is full of variety. Some stars are young, some are old, some are massive, some are small, some burn fiercely, others glow quietly. Some are surrounded by planets, others may have no planets at all, and each one is following its own path through the galaxy. The stars also create something much more important than light. They create elements. Inside stars, nuclear reactions transform lighter elements into heavier ones. Hydrogen becomes helium. In more massive stars, more complex elements can be produced. And when some massive stars die, they can release many of these elements into space. The atoms that eventually became part of planets, rocks, oceans, and living organisms did not simply appear on Earth. Many were forged through cosmic processes that occurred long before our planet existed. The universe had to build the ingredients first. Then, those ingredients had to travel through space. Eventually, they became part of new stars and planets. and much later, part of us. So when you look at a star, you are looking at more than a distant light. You are looking at one of the great factories of the universe, a place where matter is transformed, a place where energy is released, a place whose history may eventually contribute material to worlds that do not yet exist. And perhaps this is the strangest realization of all. The atoms in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, the carbon in your cells, are part of a much older cosmic story. A story that began before Earth existed, before humanity existed, before there was anyone here to look up and wonder where those elements came from. Now, as we continue traveling away from the solar system, the stars around us become more numerous. The sun becomes only one light among many. And with every step farther into the galaxy, we encounter stranger possibilities. Some stars will live for billions of years, some for trillions. Some will die violently. Some will collapse into extraordinarily dense objects, and some will leave behind remnants that are almost impossible to imagine. The stars are not simply lights in the darkness. They are living chapters in the history of the universe. Some are only beginning. Some are nearing their final moments, and some have already completed their lives, leaving behind the remains of worlds that once shone brightly. Soon, we will follow those lives further. We will see what happens when massive stars reach the end. We will encounter explosions powerful enough to briefly outshine entire galaxies. We will meet neutron stars, objects so dense that an enormous amount of matter can be compressed into a sphere only a few tens of kilometers across. And we will discover strange cosmic clocks known as pulsars. But for now, let us simply remain among the stars. The solar system is far behind us. The Earth is now only a distant memory, and all around, the galaxy continues to shine, quietly, patiently. For billions of years, we are still moving through the darkness. And now the stars around us begin to reveal another side of their existence. They are born, they shine, they change, and eventually they die. But stars do not all end their lives in the same way. Their fate depends largely on one thing: their mass. A small star may fade slowly over an extraordinary length of time. A massive star can live intensely and end its life in one of the most violent events in the universe. Massive stars consume their fuel much more quickly than smaller stars. Their enormous gravity creates tremendous pressure and temperature in their interiors. That allows nuclear reactions to proceed at extraordinary rates. The result is a brilliant star, but also a short life. A massive star can shine thousands or even millions of times more brightly than the sun. Yet its entire lifetime may be only a few million years. On the scale of the universe, that is remarkably brief. Imagine two stars born from the same cloud. One is small, the other is enormous. The small star begins a quiet existence, burning its fuel slowly. The massive star burns intensely. For a while, the massive star seems to have won. It is brighter, hotter, more powerful. But its enormous energy comes at a price. It consumes its fuel rapidly, and eventually, its interior begins to change. Inside a massive star, fusion can produce progressively heavier elements. The star's core becomes more complex. Different layers can undergo different nuclear reactions. For a time, the star can continue supporting itself against gravity, but eventually, the available energy-producing reactions can no longer provide enough support. The balance begins to fail. Gravity wins. The core collapses, and the consequences can be extraordinary. The outer layers of the star can be violently expelled. For a brief period, the explosion can become brighter than billions of stars combined. A supernovae, one of the most powerful events known in the universe. A star that may have shone quietly for millions of years can transform itself in a matter of moments. Supernovae are not simply spectacular explosions. They are also cosmic factories and distributors. The explosion can scatter elements into surrounding space. Materials forged inside the star, and elements created during the violent final stages can be released into the interstellar environment. The material then becomes part of the galaxy's future. New clouds can form from these enriched materials. New stars can eventually be born. New planets can assemble. And some of those elements may eventually become part of living organisms. The death of one star can therefore contribute to the birth of something else. In the universe, an ending is sometimes also a beginning. But not every massive star leaves the same kind of remnant. Some collapse into extraordinarily dense objects, neutron stars. Imagine taking more mass than the Sun and compressing it into a sphere only around 20 kilometers across. The result is a neutron star, an object so dense that its matter behaves in ways completely unlike ordinary matter on Earth. A teaspoon of neutron star material, if somehow brought to Earth, would have an extraordinary mass. The gravity near the surface would be enormous. The star itself would be incredibly compact. A world where mountains, if they can exist at all, in familiar forms, would be nothing like mountains on Earth. Everything is compressed by gravity. Some neutron stars rotate extraordinarily quickly, hundreds of times per second. Imagine an object with the mass of a star, spinning hundreds of times every second, while remaining only a few tens of kilometers across. The physics is difficult to picture, yet nature produces these objects. Some rapidly rotating neutron stars emit beams of radiation from their magnetic poles. As the star rotates, those beams can sweep across space. If one of them happens to point toward Earth at regular intervals, we can detect a pulse, again and again and again. These objects are called pulsars. Pulsars can be extraordinarily precise. Their regular signals can behave almost like cosmic clocks. Some pulsars rotate with remarkable stability. Astronomers can measure their timing, study their environments, and use them to investigate phenomena that would otherwise be extremely difficult to observe. A pulsar is therefore more than a strange star. It is a message arriving from deep space, a repeating signal, a cosmic rhythm. Imagine being far from Earth, in the darkness between stars, and detecting a pulse arriving at precisely measured intervals. One beat, then another, a distant remnant, still turning, still sending its signal into space. Not every star ends in a neutron star. Stars similar to the Sun follow a quieter path. When a star like our Sun eventually reaches the end of its normal life, it sheds its outer layers. The remaining core becomes a white dwarf. White dwarfs are extremely compact. They contain a large fraction of a star's mass, compressed into an object roughly comparable in size to Earth. The material inside is supported by quantum mechanical effects rather than ordinary gas pressure. The result is a strange kind of stellar remnant, no longer producing energy through normal hydrogen fusion, yet still extremely hot at first. A newly formed white dwarf can glow intensely, but without a continuing source of nuclear energy, it slowly cools, very slowly, over immense periods of time. The white dwarf becomes dimmer. Its future is one of gradual cooling rather than violent destruction. And then there are the smallest stars, red dwarfs. They are among the most common stars in the galaxy. They are relatively cool. They are faint, and they consume their fuel incredibly slowly. That makes them extraordinary in another way. They may remain active for trillions of years. A red dwarf could begin shining and continue doing so long after stars like the Sun have completed their lives, long after many massive stars have exploded, long after countless generations of planetary systems have come and gone. These small stars may become some of the last significant sources of starlight in the universe. When we think about the night sky, we often imagine the stars as though they all belong to the same generation. But they do not. Some stars formed recently, some formed billions of years ago, and some of the oldest stars in the universe existed long before the Sun was born. There are stars whose ages approach the age of the universe itself. They formed when the cosmos was young, before the Milky Way had reached its present form, before the Sun, before Earth, before any life we know. Looking at such a star is almost like looking toward the beginning of cosmic history. The light from these ancient stars has traveled for billions of years before reaching us, and within that light, we can find clues about the conditions of the early universe. The chemical composition of ancient stars can tell us about what elements existed when they formed. Some contain very little of the heavier elements that became more common later. They are remnants of an earlier cosmic era. And this brings us back to something even closer to home. Us. The human body is made from a remarkable collection of elements: hydrogen, carbon, oxygen, nitrogen, calcium, iron, and many others. But these elements did not all originate in the same place. Some of the simplest elements were created in the early universe. Many heavier elements were produced later inside stars, or during catastrophic stellar events. The calcium in your bones, the iron in your blood, the carbon in your cells belong to a history much older than Earth itself. Before our planet existed, these atoms were already traveling through the cosmos. They may have been inside ancient stars. They may have been scattered through explosions. They may have become part of clouds of gas and dust, and eventually they became part of the world where life emerged. In that sense, the history of the stars is also part of our history. The universe built stars. Stars transformed matter. Stellar deaths scattered that matter. New stars and planets formed. And eventually, on one small planet, some of those elements became alive, and those living organisms eventually became capable of looking back toward the stars and wondering where they came from. The stars around us continue to shine. Some are young, some are ancient, some are enormous, some are tiny, some will live for only a few million years. Others may continue for trillions. Some will explode. Some will collapse. Some will slowly cool. And some will simply continue shining long after the familiar stars of our night sky are gone. But there is another question waiting for us. If stars can have planets, how many worlds are actually out there? For most of human history, we knew of only one planetary system, our own. Then, astronomers began finding something extraordinary. Other stars have planets too. Thousands have already been discovered, and the galaxy may contain far more. So now, we leave the lives of the stars behind for a moment. We turn our attention toward the worlds that orbit them, worlds that may be hot, frozen, stormy, dark, or perhaps, in rare circumstances, strangely familiar. Beyond our solar system, the galaxy is filled with planets waiting to be discovered. For most of human history, we knew of only one planetary system, our own. The sun, the planets, the moons, everything we could see in the night sky appeared to belong to a universe of distant stars. But we had no direct evidence that those stars possessed worlds of their own. Then, that began to change. Today, we have discovered thousands of planets orbiting other stars. Exoplanets. Worlds that exist beyond our solar system. Some are enormous. Some are smaller than Earth. Some orbit extremely close to their stars. Others travel through much colder regions. And some exist in planetary systems that look remarkably different from our own. The discovery of exoplanets changed the way we think about the galaxy. Planetary systems are not necessarily rare. They appear to be common. Stars can form with planets around them, just as our sun did. And when we look at the night sky, every star may represent not simply a distant light, but potentially an entire planetary system. Some exoplanets orbit their stars incredibly quickly. A planet can complete an entire orbit in only a few days. Imagine a world where a year, the complete journey around its star, lasts less than a week. From our perspective, that seems almost impossibly fast. But if the planet is close enough to its star, such an orbit is perfectly possible. Some of these worlds are known as hot Jupiters. They are giant planets, often comparable in size to Jupiter, but orbiting extremely close to their stars. Their atmospheres can reach extraordinary temperatures. Their dayside surfaces can become intensely heated by stellar radiation, and their proximity to their stars can produce dramatic atmospheric conditions. Other exoplanets are even stranger. Some are so close to their stars that they may be covered in molten rock. Their surfaces can reach temperatures far beyond anything naturally experienced on Earth. Some may have atmospheres dominated by vaporized minerals, worlds that would look nothing like the blue planet beneath our feet. And yet, not every planetary system is chaotic. Some stars possess several planets. A single star can have multiple worlds, each following its own orbit. Some may be rocky, others may be gas giants. Some may be close to the star, others may orbit farther away. The architecture of each system can be completely different. Our own solar system contains 8 major planets, but other systems do not have to follow the same arrangement. Some have compact groups of planets. Several worlds can orbit much closer to their star than Mercury does to the Sun. Others contain giant planets far from their stars. Some systems appear to have planets locked into special orbital relationships. The galaxy is full of different solutions to the same fundamental problem. How does matter organize itself around a star? And there may be another category of worlds, planets that do not orbit stars at all. Rogue planets, free-floating worlds traveling through interstellar space. They may have been ejected from their original planetary systems, or formed through processes we do not yet completely understand. Without a nearby star, their surfaces could be extremely cold. Their environments would be very different from those of ordinary planets. And yet, some rogue planets may retain internal heat. Some could potentially possess subsurface environments, protected beneath thick layers of ice. The existence of such worlds reminds us that a planet does not necessarily need a star to exist. A planet can become a traveler, moving through the darkness between stars, without a sunrise, without a sunset, without a familiar day-night cycle created by a nearby sun, a world forever traveling beneath a black sky. But when astronomers search for potentially habitable planets, they often begin with a particular concept: the habitable zone, a region around a star where temperatures could, under suitable atmospheric conditions, allow liquid water to exist on a planet's surface. It is sometimes called the Goldilocks zone. Not too hot, not too cold. But that description can be misleading. Being in the habitable zone does not guarantee that a planet is habitable. A planet's atmosphere matters enormously. Its pressure matters. Its composition matters. Its magnetic environment may matter. Its geological activity can matter. Its relationship with its star matters. Even the planet's history can determine whether liquid water remains stable on its surface. Earth is not habitable simply because it happens to be at the right distance from the sun. Our planet has a complex atmosphere, liquid oceans, a magnetic field, active geology, a stable relationship with its star, and countless other conditions that have interacted over billions of years. Change one part of that system, and the result could be very different. Atmospheres can completely transform worlds. Venus is an excellent example within our own solar system. It receives less sunlight than Mercury, yet its dense atmosphere traps heat so efficiently that it becomes the hottest planet. An atmosphere is therefore not just a thin layer surrounding a world. It can determine the conditions at the surface. On an exoplanet, the atmosphere may be very different from anything we know. Some planets may have thick hydrogen envelopes. Others may possess atmospheres rich in carbon dioxide. Some may have clouds of unusual materials. Others may have almost no atmosphere at all. Each possibility creates a different world, and astronomers have begun studying some of these atmospheres. When a planet passes in front of its star, a tiny amount of starlight can pass through the planet's atmosphere before reaching our telescopes. Different molecules absorb different wavelengths of light. By analyzing those patterns, scientists can sometimes determine which gases may be present. It is an extraordinary technique. A planet may be hundreds, or even thousands, of light years away. We cannot travel there. We cannot photograph its surface in the way we photograph Earth. We cannot collect samples directly, and yet, its atmosphere can leave a tiny fingerprint in the light of its star. Imagine that, a distant world, far beyond the reach of any spacecraft we could currently build, passing silently across the face of its star, and hidden within the starlight, a clue, a chemical signature, a faint alteration in the spectrum, a message carried across the darkness. The more exoplanets we discover, the more obvious another fact becomes. Planetary systems are common throughout the galaxy. Our solar system is not unique simply because it contains planets. It is one example among many. There may be billions of planetary systems in the Milky Way, and each could contain worlds we have never imagined. Some planets may be larger than Earth, some smaller. Some may be covered in oceans. Some may be frozen. Some may have thick atmospheres. Some may have almost none. Some may orbit multiple stars. Others may travel alone through interstellar darkness. And somewhere among all those possibilities, there may be worlds that look surprisingly familiar. Rocky planets, temperate climates, liquid water, atmospheres, clouds, perhaps even environments capable of supporting life. We do not yet know how common such worlds are. The search continues, but there is something important to remember. Finding a planet in the habitable zone is only the beginning. Finding water is not the same as finding life. Finding an atmosphere is not the same as finding biology. And finding a potentially habitable world does not mean that anyone lives there. Astronomy must separate possibility from evidence. That distinction is important. Still, the search itself changes us. Because when we look for planets around other stars, we are no longer asking whether Earth is the only world. We are asking how many worlds might exist. How many places could have their own histories, their own skies, their own oceans, their own mountains, their own sunsets. If anything, there is alive to see them. And perhaps one day, future telescopes will become sensitive enough to study smaller and more Earth-like planets in much greater detail. We may learn more about their atmospheres. We may discover unexpected chemistry. We may find worlds that challenge everything we assumed about habitability. And perhaps, one day, we may encounter evidence that something living exists somewhere beyond Earth. For now, the answer remains unknown. But the night sky has changed. The stars are no longer merely distant points of light. We know they can possess worlds. And if the galaxy contains hundreds of billions of stars, then The number of planets may be almost impossible to imagine. We began this journey on Earth. Then we traveled to the moon, past the sun, across the planets, through the moons, beyond the icy worlds, and finally, out among other stars. Now, the scale becomes larger again, because all of these stars, all of these planets, all of these systems belong to something much larger, a galaxy, our galaxy, the Milky Way. From far away, the Milky Way would appear as an enormous spiral of stars, a vast structure containing our sun, our solar system, and everything we have explored so far. But even the Milky Way is only one galaxy. Beyond it, there are countless others, and beyond those, more distant structures still. So now, let us turn around, not toward one planet, not toward one star, but toward the enormous structure that contains our cosmic home, the Milky Way, and everything beyond it. The stars are no longer isolated points of light. From our position among them, a larger structure begins to reveal itself. The Milky Way, our galaxy, a vast collection of stars, gas, dust, planets, stellar remnants, and dark matter, all held together by gravity. And somewhere inside this enormous structure, there is a small yellow star, the sun, and around that star, a small blue world, Earth. The Milky Way is a spiral galaxy. From far above its disk, we would see enormous curved arms extending outward from the central region. These spiraled structures contain vast numbers of stars, along with clouds of gas and dust, where new stars can form. Our solar system is located within one of these spiral arms. Far from the crowded central region, in a quieter part of the galaxy. From Earth, the Milky Way appears as a pale band stretching across the night sky. Under a truly dark sky, it can be astonishingly bright. What looks like a cloudy river of light is actually the combined glow of enormous numbers of distant stars. Most of them are too far away to be seen individually with the naked eye. Together, they create the luminous structure that gave our galaxy its name. The Milky Way contains hundreds of billions of stars. Our sun is only one of them. One ordinary star among an almost unimaginable number of others. Some are larger, some smaller, some younger, some older, some surrounded by planets, some already dead, some still being born. And somewhere within the galaxy, there is a central region far more crowded than the neighborhood around our sun. At the heart of the Milky Way lies a supermassive black hole. It is called Sagittarius A*. Its mass is millions of times greater than that of the Sun. Compared with the scale of the entire galaxy, even this enormous object occupies only a tiny region. And yet, its presence strongly influences the motion of stars near the galactic center. If we could travel toward the center, the sky would become increasingly crowded. Stars would appear closer together. More sources of light would fill the darkness. The environment would be very different from the quiet region where our solar system resides. But the distances would still be enormous. Even inside our own galaxy, space remains overwhelmingly vast. Light takes tens of thousands of years to cross the main disk of the Milky Way. That means the galaxy is not simply large. It is large on a timescale that completely overwhelms human experience. A beam of light, moving at the fastest speed nature allows, still needs tens of thousands of years to travel from one side of the galaxy to another. Think about what that means. Human civilization has existed for only a tiny fraction of that time. Written history covers only a few thousand years. The first cities are extremely recent compared with the age of the galaxy. And yet, the Milky Way has been evolving for billions of years. Stars have been born. Stars have died. Planets have formed. Worlds have disappeared. And the galaxy has continued changing. Our solar system is therefore not separate from the history of the galaxy. It is part of it. The material that formed the Sun, the planets, and eventually Earth was part of the larger galactic environment. Our system formed from material that had already been processed by earlier generations of stars. The galaxy existed long before us, and the galaxy will continue long after us. But the Milky Way is not alone. It belongs to a larger collection of galaxies known as the local group. Dozens of galaxies are gravitationally associated within this enormous region of space. Some are large, some are small, some are irregular, some are satellites of larger galaxies. Together, they form our local neighborhood on the largest scales. Among the most important galaxies in our neighborhood is Andromeda. The Andromeda Galaxy is one of the largest nearby galaxies to the Milky Way. It is a spiral galaxy too, and it contains an enormous number of stars. When we look toward Andromeda, we are looking across millions of light years of space. The light reaching our eyes today left that galaxy millions of years ago. This means that Andromeda is not being seen as it is now. We see it as it was in the distant past. This is one of the strangest consequences of the finite speed of light. The farther away something is, the further into its past we are seeing. When astronomers observe distant galaxies, they are also looking backward through cosmic history. A galaxy millions of light years away is a message from millions of years ago. A galaxy billions of light years away is an even older message. The universe is constantly showing us its history. We do not need a time machine. We simply need to look far enough away, and galaxies themselves do not remain fixed. They move, they interact, they can pass near one another, and sometimes they collide. Or more accurately, they merge. When galaxies merge, their stars generally do not simply crash directly into one another. The distances between individual stars are enormous. Even when two galaxies overlap, the probability of two stars physically colliding remains very small. Instead, gravity reshapes the galaxies. Their structures become distorted. Their stellar orbits change. Gas clouds can collide. New stars can be triggered to form. And eventually, the two galaxies may become one larger galaxy. And this brings us to one of the great future events in the history of our local cosmic neighborhood. The Milky Way and Andromeda are approaching one another. Over billions of years, their gravitational interaction will become increasingly important. Eventually, the two galaxies are expected to merge. The final result will be a transformed galaxy, very different from the Milky Way we see today. It sounds violent, and on the galactic scale, it is. But from the perspective of individual stars, it may be surprisingly quiet. The stars are separated by such enormous distances that direct collisions between them are extremely unlikely. Instead, the sky would change. The structures of the galaxies would slowly distort. Star orbits would be rearranged. Gas clouds would interact. And, over immense stretches of time, a new galactic structure would emerge. Imagine standing on a planet during that distant future. The night sky would no longer resemble the sky we know. Andromeda would gradually grow larger, brighter, more prominent. Eventually, its stars would spread across the sky. The familiar shape of the Milky Way would begin to change. The distinction between our galaxy and Andromeda would slowly disappear. And yet, the stars would continue shining. New stars would continue to form. Old stars would continue to die. Planets would continue orbiting their stars. Life, if it still existed, would continue beneath alien skies. The galaxy would change, but the universe would continue. There is another strange fact about looking at distant galaxies. The farther we look, the older the universe appears. We can observe galaxies at different distances and therefore see them at different stages of their history. Nearby galaxies are seen relatively recently. More distant galaxies are seen much further in the past. Some of the most distant galaxies we observe existed when the universe itself was still very young. Astronomy, therefore, gives us something almost impossible to experience anywhere else. A view through time. One telescope image can contain galaxies at different ages, different distances, different moments in cosmic history. The universe is not showing us a single present. It is showing us layers of its past. And beyond the Milky Way, beyond Andromeda, beyond the local group, there are enormous numbers of other galaxies. Some are spiral galaxies, some are elliptical, some are irregular, some contain trillions of stars, others are much smaller, some are still forming stars rapidly, others are dominated by ancient stellar populations. The observable universe contains an extraordinary number of galaxies, and each galaxy can contain enormous numbers of stars. Many of those stars may have planets. Many planets may have moons, and every world has the potential to follow its own history. The scale becomes difficult to hold in the mind. We began with one planet, then one moon, one star, 8 planets, countless smaller worlds, other stars, other planets, the Milky Way, and now an observable universe filled with galaxies. Yet, even this enormous view is not the end, because the universe itself has a history. It was younger once, hotter, denser, filled with conditions very different from those we see today. Stars formed, galaxies assembled, structures evolved, and the universe continues changing. Somewhere in that vastness, our galaxy is only one structure. The Sun is only one star. Earth is only one planet, and humanity, only one species. A very small part of an extraordinarily large story. But perhaps that is what makes looking at the universe so peaceful. We do not need to be large to be part of something enormous. We do not need to understand everything. We can simply observe and wonder and allow the scale of the universe to remind us that there is always more beyond the horizon. The Milky Way continues turning slowly through space. Its stars continue moving. Its clouds continue forming and dissolving. Its ancient light continues traveling outward. And beyond it, other galaxies continue their own long journeys. Some are colliding. Some are being born. Some are fading. Some are so distant that their light has been traveling toward us for billions of years. And somewhere inside all of this, the small blue planet where our journey began is still turning beneath its atmosphere. The same Earth, the same moon, the same sun, only now we have seen them from a much greater distance. The universe is far larger than the world beneath our feet. Far larger than the solar system, far larger than the Milky Way. And yet, everything we have explored so far is still only the beginning of the larger cosmic story. Because the galaxies themselves have lives. Stars are born within them. Stars disappear. New worlds form, and the universe slowly changes with time. So, for a moment, let us simply remain here, between the stars, looking back toward the Milky Way, a small spiral island, filled with hundreds of billions of suns, and somewhere within it, one tiny world, where someone can lie quietly at night, look upward, and wonder how much more remains to be discovered.